Assalamualaikum warahmatullahi wabarakatuh. My name is Norsyahadah from Section 4, Dr. Rizza Othman. So today I'll be explaining about production of acetone from isopropanol using Aspen Plus. So we go to Aspen Plus. So firstly, we key in all the component, isopropyl alcohol, acetone, hydrogen and water. And then we choose the thermodynamic method and RTL because for a non-random to liquid model used for calculating activity coefficient to take into account non-ideality in liquid phase. And then we perform thermodynamic binary analysis. We key in all the binary analysis specification for the component, composition and pressure, and then calculation option, and we run the simulation to get TXY plot. This is our TXY diagram for acetone and IPA. And then we go to the simulation. Firstly, we go to the main flow sheet. This is our PFD for this simulation. Firstly, we go to the feed material. We key in the temperature and pressure, and we put the composition 136.4 kilomole per hour. And then we go to the reactor. We choose R plug, which is because we have catalyst. For the temperature, we make it constant at the inlet temperature, and then we go to the configuration. This is just initial gas for number of tubes 790, and for the tube is multi-tube reactor, length 1 meter, diameter 3 centimeter, and vapor only. And then go to the reaction. This is our reaction 1. We key in the reaction. This is our reaction. So for the reaction 1, reaction class is power law. For the reactant is IPA, and the component is acetone and hydrogen. And then for the power law, not this one, input I think. For the kinetic, we put the data that given in the question. This is all the data that given in the question. And then driving force is second order in the IPA. And then we go back to the main flow sheet at the reactor. As mentioned in the question, we have catalyst. So this is the information for catalyst: back voltage 0.5 and particle size 2,500. And then we run the simulation. So for the outlet stream from the reactor is then passed through a scrubbing column. Here the vapor is contact with liquid water. This is liquid water that contact in at the scrubber, and then vapor phase outlet from the scrubber may be separated. This is the outlet phase for the vapor phase, and so or flare depending on the economics. and the liquid phase outlet from the scrubber is passed to a light gas separator. And then we go to the STWU. For the design, the purification process using shortcut distillation column. We key in all the data for the DSTWU. For the number of stages, this is just initial gas. And we key in the key component recoveries, which is light key acetone and 99.9% recovery, and heavy key 1%. We put the two condenser and reboiler for 5 bar. And then we run first the simulation to see the result. We can see this is the summary. The actual refract ratio is 1.64. Feed stages 32. Number of actual stages above feed is 31. And then as we got all the information and we go back to the DSTWU input and go to the calculation option and tick right on the generated table of refract ratio versus number of theoretical stages, and we key in the initial and final stages within the range based on the result that we got, and then we run the simulation and go back to the result to see the refract ratio profile. This is the table for theoretical stages and refract ratio. We copy this table into the Excel and we plot this graph. Firstly, we plot this graph, and then we plot theoretical stages times refract ratio for X. For Y, for X is number of stages, and we can calculate the optimum number of stages and refract ratio. As we got this graph, there is a minimum number of stages for a given separation, the use of which would require infinite reflux. There is a minimum reflux ratio for a given separation, the implementation of which would require an infinite number of stages. Between these extrema, there is a roughly exponential decrease in reflux ratio with increasing number of stages. When the y-axis in is theoretical stages times reflux ratio, instead of reflux ratio, the point will form a curve which has distinct minimum. For minimum reflux ratio, cost of the condenser and reboiler is reduced, but fixed cost is increasing due to increase in infinite number of stages. For total reflux ratio, now of stages is decreasing, but the cost of condenser and reboiler is increasing. In both of the cases, the process is not economical for separation. The optimum ratio should be lie in between both cases. The optimum ratio should be economical, optimum, and cheaper. So for this graph, the minimum in number of stages times reflux ratio versus number of stages curve occur at 29 theoretical stages. So a guess of around 32 to 40 stages for optimum number of stages and reflux ratio. And then we go back to this Aspen Plus simulation, and we go to the next question, which is obtain a simulate refract for model based on the STWU result. So we go to the refract. Firstly, we go to the main flow sheet. We just replace the STWU with a refract column. We just click on the refract and key in all the information that we got from the STWU. For the number of stages is 55, total condenser, and then we key in the operating specification. We choose reflux ratio and distillate to feed ratio. This is the data that we got from the STWU, and then we go to the stream. We key in the feed stream at stream number 7 at 32 stage, and then for the pressure, just the same with the pressure at the DSTW 5 bar, and then we run the simulation. So we got the stream result for red frag, 50,000 ton per year, which is same as desired product that we need from the question. And then we have to obtain the desired product specification using design spec option. This is based on design spec option. So we got the desired product already. So how to get the specification, design specification? We go to the red frag and go to specification, click design spec, and click new, and then we key in the design specification. For the description, we want to recover more recovery 99.9%, and for the component we choose acetone because this is our desired product. And for the feed stream, acetone in the stream number 3 from the feed stream number 7. And then we key in the vary, which is manipulated variable or adjusted variable. We choose between specification that we put in the configuration, either reflux ratio or distillate to feed ratio. So for me, I choose distillate to feed ratio for the vary. So this is the range within the data that we key in distillate to feed ratio, and then we run the simulation, and we got the answer for the stream, which is 50,000 that I already showed before. Stream number 3 actually. So this is the result. This is in kilogram per hour. You just convert it into the ton per year. So we got 50,000. It's achieved our desired product that we need. And then for next question is simulate the overall process without recycling to achieve desired purity capacity. This is just the same with the STWU without recycle. We already got the purity 99.9%. Wait, we go to the stream result. So for the acetone, this is our desired purity 99%. So it's already achieved the requirement. Also the mass flow rate. This is our mass flow rate, 50,000 in range in 50,000 ton per year. So for the last question, suggest and simulate recycling system for the process and describe the necessary step to achieve the desired purity and capacity. And then we go to the recycle, go to the main flow sheet. This is our PFD in the Aspen Plus. We recycle from liquid stream at the flash, and the vapor stream we go to the DSTWU. So for the result of this simulation, which is recycle, we got the desired uh, purity and capacity is 99.9, as stated in the question, and 107. When we calculate the mass and energy balance, we got 107. So for the recycle, we got the same result. So we achieved the desired purity and capacity. Yeah, this is 50,000. So that's it from me. Thank you and Assalamualaikum.